The final quantity that we can talk about making angular or making rotational is momentum. We learned a few chapters ago that momentum is equal to mass times velocity. As a matter of fact, we learned that that was the definition of momentum. Momentum equals mass times velocity. So angular momentum is very similar. Angular momentum is defined by its definition. This is one of the few quantities that we have made angular that is not a Greek letter. Instead, angular momentum is a capital letter L. I can't tell you why they choose capital letter L. We know that the rotational equivalent of mass is moment of inertia, and the rotational equivalent of velocity is angular velocity. So L, the angular momentum, is equal to I, the moment of inertia, times omega, the angular velocity. Whatever the direction is of the angular velocity, that's the direction of the angular momentum. The units, as we can tell, for this are kilogram meters squared, and the units for omega are radians per second. And when we multiply kilogram meters squared times radians per second, we get kilogram meters squared per second. Now that's a little bit weird. Where did the radians go? Well, radians are a weird unit. Anytime you multiply them by any other unit, radians just disappear. So the unit for angular momentum is kilogram meters squared per second. It is a vector, as you can tell by the vector symbol. And again, its direction is clockwise or counterclockwise. So let's calculate the angular momentum of this system here. This system is one we've seen before, where there are two particles attached to a light, rigid rod, and we're rotating it about the center of that rod. We want to know the angular momentum of the system if the speed of each particle is 5 meters per second. We know angular momentum is equal to I times omega, and it is a vector. So let's first calculate I. We've done this once before, but in case you don't remember, we'll go through the calculations again. I, just like mass, can add. So we'll add the moments of inertia of these two particles. The problem specifically tells me to neglect the rod's mass so it does not have a moment of inertia. Particles have a moment of inertia equation of mr squared. The r is the same for these two particles because they're the same distance from the axis of rotation. So I can factor that out. So I end up with the m1 plus m2, which is 7 kilograms, times r squared. R is 0.5 meters. So we square that, and we end up with a moment of inertia of 1.75 kilogram meters squared. So we'll plug that into our equation. But immediately I notice that I'm not given an angular speed, because the unit of the speed that I'm given is meters per second. Instead, I'm given a linear speed. Fortunately, we know that the angular speed is just the linear speed, or the tangential speed, divided by the radius. So we'll plug in the 5 meters per second divided by the 0.5 meter radius, and we find that the angular speed of these particles, or of the whole system, is 10 radians per second. So then the angular momentum, which is I times omega, or 1.75 kilogram meters squared times 10 radians per second. That gives me 17.5 kilogram meters squared per second. Now we know angular momentum is a vector, so it has a direction. Looking at my diagram here, it is clear that this system is moving counterclockwise. And so that's the direction I will give. One more problem with this. Example number 16 asks us to calculate the angular momentum of Earth that arises from its spinning motion on its axis. We are treating Earth as a uniform solid sphere. And then we want to know about the angular momentum of Earth that arises from its orbital motion about the Sun, treating Earth as a point particle. The problem gives us the mass of the Earth and the radius of the Earth, and also the average distance between the Sun and the Earth. Again, the thing that will change for these two calculations is the equation that you use for the moment of inertia. For one, you'll use for a solid sphere, and the other one you'll use the equation for a particle, mr squared. Finish this problem on your own and bring it to class with you, along with the work, tomorrow.